All right, good. So welcome to week 5 already, if you can believe it. It's a big week for us. Homework 3 is due Wednesday at 4:59, so before the test, which leads me to the first big point there. The first test is on Wednesday. 13 questions, just like the practice test. Multiple choice, but you have to show your work. Combination of conceptual and more mathematically rigorous questions. Make sure you make your own formula sheet. So I would recommend doing this before 4:30 on Wednesday. It's actually a good way to study, right? You can kind of put all the formulas on there, whatever you want. And as you write them down, make sure you know what everything means on them and things like that. So it's a way to kind of study, I think. You organize your thoughts, put it on your formula sheet. Okay, any questions about this? Okay, so what I want to do today is kind of just finish up a little bit with homework 3, kind of tie up some loose ends there, and then we'll go over the practice test, and I can give you some hints along the way. Okay, sounds good? Yep, good. So a little bit of a review here. This is what we talked about last time. Sum of the forces equal to 0. That just means all the forces are balanced. It doesn't mean there's no forces. It means whatever force is to the right is balanced by whatever force is to the left. Whatever's up is balanced by whatever's down. So these problems are called statics problems. So I want to do a couple more examples of that today. The next one, sum of the forces is ma. That's a dynamics problem. So really using Newton's second law to solve problems. The vector sign just means consider the x direction independent from the y direction. And we didn't quite mention this last time, but the weight force, we've seen the weight force before, it's actually equal to m times g. So if you take the mass, multiply it by 9.8 meters per second squared, you get the weight. And we can solve some problems using that too. Okay, so first thing, let's look at some more homework questions. Good. So this is from homework 3. So basically the test goes chapter 1, chapter 2, chapter 3, and 4, and just the first couple of sections of chapter 5. So we haven't seen these yet. So this we've got 3 ropes in this picture tied to a small, very light ring. 2 of the ropes are anchored to the walls at right angles, so rope 1, rope 2. What are T1 and T2, the magnitudes of the tensions in the first 2 ropes? And we're given what this one is down here. Okay, so this is a statics problem. All the forces are balanced. So let's take a look at it. Good. Definitely need a picture for this one. So we've got T1 over here. That's to the left. T2 over here. And then we got this one over this direction. I'm just going to call it T3. 100 newtons. And I also know this is 30 degrees. So whatever is up has to be balanced by whatever's down. Whatever is to the left has to be balanced by whatever's to the right. And I don't think we got to this one, did we, last time? I don't think we quite did. Okay, we did a similar one, but not this one. Okay, so I know this T3 has a part in the y direction, and it has a part in the x direction. So I know T1 has to be equal to T3 in the x. That's balancing horizontal forces. And then I also know that T2, which is up, has to be balanced by T3 in the y direction. So luckily T3 is given, the angle is given. I can figure out what T3x and T3y are just from the trigonometry. And then the physics part is, once I get T3x, T3y, then I can figure out T1 and T2. Okay? Good, so the sine of 30 is the opposite side over the hypotenuse. And then the cosine of 30 is the adjacent side, which turns out to be T3x, over the hypotenuse, which is T3. So T3 sine of 30 is T3 in the y direction. Anybody know what the sine of 30 is? That's one that'll save you some time in your life if you know it, at least in physics. Sine of 30 is a half. So this turns out to be 50 newtons. Whoops. And then T3 cosine 30 is T3 in the x. So cosine of 30 is a square root of 3 over 2, which turns out to be 0.866 or so. So this is about 87. Okay, or you could use your calculator if you don't remember those. The sine of 30 is an easy one to remember though. Okay, so balancing forces. That's what T3 x is, and then you know it's equal to T1, and that's what T3 y is, and then you know it's equal to T2. Okay. All right. Any questions on this one? All right. So let's look at a few more of these. Good. So this is kind of a neat one. This is actually going on, you know, in your body, balancing forces from tendons and bones on kneecaps, things like that, which you can't see. Good. So when you bend your knee, the quadriceps muscle is stretched. So you can imagine yourself doing that. This increases the tension in the quadriceps tendon, which is the tendon right here, and attached to the kneecap, which is the patella. Okay? Which in turn increases the tension in the patella tendon that attaches to your kneecap, attaches your kneecap to your lower leg bone. And that's right here, this patella tendon. Okay, good. Let's see. Simultaneously, the upper leg bone, which is the femur, as you can see here, the femur pushes down on the patella. So this tendon stretches this way, the patella tendon goes this way. In turn, that causes the femur to push down on the patella. And the figure shows how these parts are joined together, and you actually have an angle here, 42 degrees. So what size force does the femur exert on the kneecap if the tendons are oriented as shown in the picture, and each has a force of 60? So it's really just like we did, right? The problem that we just did. Not exactly the same, but pretty close. We've got one force that's up, that's the quadriceps tendon. The patella tendon is down at some angle that makes it a little bit trickier, but not too bad. So these are forces on the patella. There's also a force on the patella from the femur. All the forces are balanced, though. So from this information, we should be able to solve this. Definitely need a nice picture, which I'll construct right now. Again, this is balancing forces. Okay. So we have, luckily this is 60 newtons, straight up. We have another 60 newtons, and this theta is given in the problem, 42 degrees, and we want to know what is the femur force. The thing to know though is everything is balanced. So if there's 60 up, there has to be 60 down. So this femur force, I'm just going to call it F sub F femur force. It's going to have 60 this way to balance the upward one, and then it's going to have enough to balance this force also. So this is 60 newtons at 42 degrees. We'll have to figure out exactly how much it is, though. So let me redraw this one. This is 60 newtons because it's balancing the upward force. So this 60 newtons has some this way. It does, yeah. Yeah. So this 60 newtons is here. Part of it's there. Part of it's here. And Rick is right. This one is not actually 60. So how do we know that? There's 60 newtons up, but The 60 newtons we have from this force, this direction, has a part this way. So let me actually start over with the picture because it's getting a little bit too crowded now. By the way, you're seeing this in live action, right? So this is how it goes. Sometimes you have to do that, right? Kind of start over. So we've got 60 newtons here, and we've got 60 newtons here. And then this is back to being theta. The thing that doesn't change, though, is we have to balance up with down, right with left. So the 60 newtons has a part that's this way and a part that's this way. Now this femur force, if you take into account this one that's up, we got this one to the right, this one to the right, this one to the left. Whatever we have up net-wise here, it turns out it's going to be net up because this 60 is going to be bigger than whatever this is. We'll have to put it all together, but whatever net is up has to be whatever net is down. Whatever's to the right, which we'll have to figure that out too, is going to have to balance by whatever's to the left. Let's actually put these numbers on because I think it'll be helpful. This one here, which that's the patella tendon force. So force patella, I'll call it in the y direction, is force patella times the sine of theta. And this one here, force patella x, would be force patella and then the cosine of theta. So let's actually get numbers for those instead of waiting to the end, just so we see how this all works out. And this is the force patella I'm talking about. Okay, so this one, we have 60 newtons times the cosine of 42. So about 44.59. So that's to the right. This one, 60 times the sine of 42 degrees. This would be 40.15. So that's force patella y. The x direction is actually a little bit easier in this problem. The reason is there's 60 directly up. This doesn't have any part in the x direction. The only x one is this 44.59. So I know the force by the femur has to have a part that's 44.59 going this way. So this is force femur x. 44.59 newtons. So how much does this force femur y have to be then? That's the one that's a little bit trickier. Well, in the y direction right now, I've got 60 up. That's from the quadriceps tendon. And I've got a little bit down from the patella, only 40.15. So I got 40.15 down, 60 up. I still need a little bit more down. So 60 minus 40.15. That's going to be the difference. So 60 minus 40.15. 19.85 or so. That's what this one's got to be. And then when it says, sum of the forces is 0, whatever's up, 60 is up, 19.85, 40.15, that's down, those balance. And I've got 44.59 to the right, I've got to have the same amount to the left. So the net force from the femur, you've got to add those together. Now you can't just take the numbers and add them together. You've got to add them like this. Force femur x squared plus force femur y squared. And then take the square root to get the net amount. Okay, so without putting all the numbers in, that's the way to do it. Good, so we balance forces on ropes. It turns out it's a really similar situation to this, to your knee joint. Okay, excellent. Any questions on this one? All right, good. One of our former students is Diane. I think she does this sort of thing. Physical therapy and all that sort of thing. Oops. So this is a dynamics problem. An early submersible craft for deep sea exploration was raised and lowered by a cable from a ship. When the craft was stationary, the tension was 550 newtons. When the craft was lowered or raised at a steady rate, the motion through the water added an additional 1,800 newtons drag force. And we want to know what was the tension in the cable when the craft was being lowered to the seafloor, and what's the tension in the cable when the craft was being raised from the seafloor. Okay? So when it was stationary, they're saying the tension is 550 newtons. And then when it's lowered or raised, there was this additional drag force. So we'll have to take a look at which direction the forces are. Okay? Let me put this on the screen. So when it's just stationary, we have tension of 550 newtons. 5,500 newtons. So that's got to balance the weight. So the weight is also 5,500 newtons. Okay. One other thing that we know about this is kind of a new part. We can get the mass from this if we wanted to. So the weight is m times g. So if you take the weight divided by g, that will give you the mass. Okay, that's just a little bit more information. So raised and lowered at a steady rate. So let's take a look at that. Maybe we'll just do the first part here. So when it's being lowered to the seafloor, let's look at all the forces on it actually. So when it's being lowered, there's still tension. There's a drag force because it's being lowered, so the drag force is the opposite direction, and then we still have the weight. So how much is the acceleration for part A? Kind of a trick question. Maybe a better question is there an acceleration in the first part? Zero, right. Steady rate means all the forces are balanced. So really this is, I said it's kind of a dynamics problem, but really it's more like a statics problem. The acceleration is zero. The forces are still balanced. Now to lower this in the first place, the weight had to be bigger than whatever force is up. But we're just looking at a snapshot of what's going on right now as it's being lowered. So whatever is down has to be equal to whatever's up because the acceleration is zero. Okay? So weight down is equal to tension plus the drag force. This part we don't actually need to do the problem. I just wanted to throw it in there to get that topic started. Okay, so this is balancing forces, and we're trying to figure out the tension. So a little bit of algebra then. Weight minus drag force is equal to tension. So the weight is whatever the weight is. It's always going to be this on the Earth. 5,500 newtons minus 1,800 newtons. That's the tension when you're lowering it at a constant speed. Okay, so whatever that turns out to be, 3,700 or something like that. Okay, good. Any questions on the first part? Now the key to the second part is knowing which direction the forces are. So when you're raising it at a constant speed, which is being done here, what's the tension when it's being raised from the seafloor? So when it's being raised, really the key is this part. So which forces are up? Well, we've got tension. Which forces are down? Well, the weight's always going to be down. But if you're moving it up, the drag force is down in this case. So tension's got to be equal to drag force plus weight, and then you can calculate the tension. Okay. All right. Good. So in a way, on the way down, the drag force is helping you out, right? The tension's not as great. When you lift it up, the tension's going to be more. Okay. Any questions on that part? Okay. Okay, so this is the one where we have a dynamics problem. That you can't see this. Okay, so the forces are given in this picture, and we want to know what is the acceleration in the x direction, and there might be another part down here. No, okay. There is no acceleration in the y direction. The reason is there's 3 newtons up, 3 newtons down. There is no y acceleration. Now in the x direction, there's 2 newtons to the left, but there's 4 newtons to the right. So we do have a net force in the x direction. So we could use Newton's second law to figure that out. We know the mass is 1 kilogram also. So as far as the x direction goes, we've got 4 newtons this way, 2 newtons back that way. This is just looking at the x direction. Mass 1 kilogram. Okay, so net force, MA, and then you got to put in whatever goes in this box. And this is just in the x direction. Well, we got 4 newtons to the right, minus 2 newtons back to the left. So the net force is 2 newtons. And then I can solve for the acceleration. Mass is 2 newtons divided by 1 kilogram. So, 2 meters per second squared. Remember, a newton is a kilogram meter per second squared. Kilograms cancel out. Okay? Good. Excellent. We don't know what these forces were, but we just know the directions of them. Any questions on that one? Okay. So maybe we'll make this the last one, and then if you have any questions, maybe if there's time at the end, we can talk about it. Or you can send me an email. How much force does a 78 kilogram astronaut exert on his chair while sitting at rest on a launch pad? Okay, so sitting at rest, there's a normal force, and then there's the weight. So this is the free body diagram of the astronaut. Oh, sorry. Thanks, Rick. Okay, so this is the free body diagram of the astronaut. Like, pretend I'm an astronaut. Use your imagination for that one. I'm sitting in the chair. There's forces on me. The weight is the earth pulling me down. The normal force is the force from the chair on me. So normal force from chair on me. Now there's also a normal force from me onto the chair. Those are third law pairs. So the normal force from the chair on me is up. There's a normal force from me onto the chair, which is down. They really are asking for that, but it's the same thing as the normal force from the chair on me. When it says how much force does the astronaut exert on the chair, it's the same thing as the normal force on the chair from me. So I can figure that out, and then I know it's the same thing. Okay, so just sitting there, no acceleration, not even moving in this case, this has to be equal to this. So normal force from chair on me, I'll leave off all the subscripts, is equal to mg. So it's the mass, 78 kilograms. That's the unit of mass. Multiply it by 9.8 meters per second squared to turn it into a force. Okay, so 78 times 9.8. 764.4 kilogram meter per second squared, which are newtons. Okay, so just sitting there, that's what the force is on me. How much force does the astronaut exert on the chair while he's accelerating straight up at 11 meters per second squared? Same thing, the normal force from the chair on me is going to be the same as the normal force from me onto the chair. Now you don't usually think about it like this, but really, if you're accelerating up and you're sitting in the chair, I mean, ultimately, really, it's the rocket that's pushing you up. But if you just looked at the forces directly on the astronaut, there's just the normal force and the weight. So why did I draw the normal force bigger than the weight? Well, what happens if the normal force is bigger than the weight? What do we get? Say that again? Well, if it was the other way around, yeah, the acceleration would be down. But since this is bigger than this, we have an acceleration that's going to be up. I drew it on purpose bigger because they're telling us we got an acceleration this way. And then whenever there is an acceleration, there has to be a net force. So if the acceleration is up, that means there has to be a net force which is up. And here there is. The normal is bigger than the weight, so there is a net force. Okay, so here's what we know. We also know the mass, 78 kilograms. We just figured out the weight above. This one's 764.4. I'm doing all this because on the test, if I had this picture, I would give myself 4 out of 10 right now. We're trying to figure out the normal force. So how do I know to use Newton's second law? Well, this problem involves forces and acceleration and masses, so that's a hint, a clue really to use Newton's second law. Net force, ma, and then we got to supply this stuff. So right now I'm at 6 out of 10 points. I've got everything written down, a picture, there's the correct concept to use, and I've got to fill in the blank here. So I'm going to do normal minus mg. These are the actual forces from the picture here. Okay, so now I'm up to 8 out of 10 probably. Now I've got to do a little bit of algebra. ma plus mg is the normal force. Yeah, probably 9 out of 10. And then now we've got to actually put the numbers in. So 78 kilograms times 11 plus 78 kilograms times 9.8. That's got to be the normal force. Okay, so without putting any numbers in, that's the weight that you do it. Like around 1600 or something like that. Okay, so the bigger and bigger the acceleration, the bigger and bigger the normal force is. Okay, excellent. Any questions on this one? All right, so let's take a look at the test then. So it's on Bright Space. And it's, I think there's 11 questions here, 11 on the actual test. Make your own formula sheet, both sides, regular piece of paper. Put whatever you want on there. And got the whole time to do it. And the answers are on the last page. So it's a combination of these conceptual ones and ones with numbers. So show all your work for credit. A bucket is being lowered by a very light rope with a constant downward velocity. The tension must be equal to the weight, less than the weight, greater than the weight. Well, in this problem, constant velocity means the acceleration is 0. So we're seeing what's going on right at this instant. constant downward velocity. That means the acceleration is 0. There's no net force. So it's got to be equal to the weight. My explanation is constant velocity means no acceleration. Therefore, there's no net force. The force up has to be equal to the force down. I just said it in words. You could do a picture. You don't even have to say any words. You could completely just do it with numbers and a picture too. However you want to explain it. Now on the other hand, if this bucket was accelerating up, then the tension would have to be bigger than the weight. If it was accelerating down, the weight would have to be bigger than the tension. That sort of thing. Okay? So take a look at that. I mean, I gave you this situation. On the actual test, you're not going to have the same situation. You'll probably have a similar problem, though. Okay, so think about the alternatives. Right? Okay? Hint. Your first hint of the semester. Any questions on that one? All right. Good. A rock from a volcanic eruption is launched straight up into the air with no appreciable air resistance. Which of the following statements about the rock while it's in the air is correct? So you launch it up into the air. Let me give you a little refresher on this. On the way up, the velocity is positive, gets to the highest point, the velocity is 0. On the way down, the velocity becomes negative. So velocity versus time. We'd have something like this, right? So on the way up, the velocity is positive. The highest point velocity is 0. The way down, the velocities are negative down here. The whole time, after it's launched, this is the free body diagram. On the way up, this is the free body diagram. At the highest point, this is the free body diagram. On the way down, this is the free body diagram. Okay. So we want to know something about this. The acceleration is downward at all points of the motion. So, so far that's the only one, but that is completely correct. The acceleration is down at all points. No matter what, even at the highest point, the acceleration is down. At the highest point, gravity is still there, right? So it doesn't just get to the highest point and then just stay there. The force of gravity is still pulling it down, so the acceleration is still negative 9.8 meters per second squared. But let's read through the other ones. On the way down, both the velocity and acceleration are down. At the highest point, the velocity and acceleration are 0. So at the highest point, the velocity is 0. Sorry, you can't see. So at the highest point, the velocity is 0, but the entire time, the acceleration is down. The whole time, there's a force down, even at the highest point. So it's not B. Throughout the motion, the acceleration is down, and the velocity is always the same direction as the acceleration. So that's not true, because on the way up, the velocity is up, but the acceleration is down. So that's not true. D, on the way up, the acceleration is down, velocity is up. At the highest point, the velocity and acceleration are 0. Again, that one's not right because the acceleration, the whole time, is down. And then E, the acceleration is down all times except for at the highest point where it's 0. So that's not true either, right? The acceleration is always negative 9.8. Just pretend you take something, you put it here, it's not moving for an instant, but then it accelerates down because gravity's there, always pulling it down. So A is the correct choice. Okay, any questions about that one? All right. So you'll see something similar to that. The acceleration due to gravity on the moon is 1/6 of that on the Earth. And the moon has no atmosphere. If you hit a baseball on the moon with the same effort and therefore the same speed and angle as the Earth, how far would the ball travel on the moon compared to the Earth? Okay, so this goes back to the projectile motion chapter. Yeah, thank you. Excellent. So I'm drawing this situation. This is the overall velocity. This is the angle. We did a few problems on this, like the largest pass ever in NFL history, that sort of problem. We came up with something called the range equation. So the range, initial velocity squared, sine of 2 theta, and this is the overall angle, this is the overall velocity. Not the x or y, the overall. And then divided by g. So we use this equation to predict the range just based on the overall velocity and the angle. So the g of the moon is 1/6 the g of the Earth. So if you make g 6 times 1/6 as much as the Earth, then the range is going to have to be 6 times more. The problem that we did, we actually calculated it, right? The distance between the moon compared to the Earth, and it's 6 times greater on the moon. I think it was a golf ball on the moon, actually, too. Do you remember that problem? Homework 2, I think it was.
So you just take 6 times Earth's?
1/6 as much. So this would be the Earth, range on the Earth. So if you want to, you could do like this. The range on the moon would be same initial velocity, same angle, but now it's g divided by 6. So then this would be 6 times the Earth's range. Right, because it's g over 6. So you can use this equation to get the range. This is a conceptual way of using the range equation. I think the actual one in the test, you might use the range equation for an actual problem with distances and angles and things like that. So just be familiar with the range equation. It'll make your life a lot simpler. So there it is right there. And this g, remember, it's just 9.8 meters per second squared. Okay, great. Any questions on that one? Okay, so far so good, I think. There. Okay. A ball is thrown downward from the top of a building with an initial speed of 25. It strikes the ground 2 seconds later. How high is the building, assuming negligible air resistance? Okay, so this really goes back to free fall in chapter 2. So for free fall, let me write this stuff down. Free fall means either going up or coming down, remember. Regardless, we know the acceleration, negative 9.8. So in this problem, thrown downward. So initial velocity in the y, negative 25. Remember, it's being thrown downward. It strikes the ground 2 seconds later, so it heads this way. This takes 2 seconds. How high is the building? Okay, so this is the y displacement. That will actually come out to be negative. In this problem, we just want to know the magnitude of it, right? How high the building is. So we've got all the kinematics equations to work with. Velocity final is equal to velocity initial plus at. Velocity final in the y squared, velocity initial in the y squared, 2a delta y. And then finally, delta y, initial velocity in the y times time, plus 1/2 at squared. Those are the tools we have to work with. And we're trying to figure out delta y. So from a practical standpoint, you're trying to figure out delta y. This one probably comes to your eye the quickest, right? Because here's one that delta y is equal to something else. We don't even have to do any algebra for this one. We know the initial velocity, we know the time. you have to remember that you also know the acceleration and the y because we're in free fall. So we could use the third one there to figure out what delta y is. You could do this another way, maybe. You could figure out the velocity right before it hits the ground from the first one, and then you could use that velocity in the second equation to figure out delta y, because then you'd know everything except for delta y. So this is probably the quickest way to do it. You could use a combination of the first one and the second one, though, if you wanted to. So why am I using that one? It's because based on what I know and what I'm looking for, this one will work out for me. So minus 25 meters per second, and then this is for 2 seconds, and then plus 1/2 negative 9.8, and then times t squared, so 4 seconds squared. Sorry, I'm out of room here. Okay, so put all that together, you'll get delta y. Yeah, I guess we could do it. This would be like minus 50 meters. This term over here would be minus, let's see, 19.6 meters. So about negative 70 or so. We just want the height, so we want the magnitude of this. So it's good. Well, that's one of the answers, 70. Okay, good. Excellent. Any questions on this one? Now this one, they actually tell you you're throwing it downward at 25 meters per second. It could be a problem where you actually just drop it. Now if you just drop it, don't forget, if you're just dropping something straight down, the initial velocity would be 0. It's never going to say, don't forget it's 0, but you have to bring that to the problem, right? Okay. Suppose an object is moving with a constant velocity. Okay, good. So think everything that means. Constant velocity. That means the acceleration is 0. That means there's no net force. Okay, so the acceleration is constantly increasing. So that doesn't make any sense. The acceleration is 0. Okay, so far so good, right? The acceleration is constantly decreasing. So no. Constant velocity means the acceleration is 0. The acceleration is a constant non-zero value. So that's not true. I mean, if they said that the velocity was constant, that would be true. That's the only thing that's actually constant. So the acceleration is equal to 0. You could say something like the acceleration is the change in velocity divided by the amount of time. There is no change in velocity, so therefore there is no acceleration. Okay? Good? Excellent. So now if there is an acceleration, think about what that means as far as the test goes. Now if there is an acceleration, that means the velocity is changing then, right? That's the other side of it. This is velocity is not changing, so the acceleration is 0. What if the velocity is changing? What does that mean? So make sure that you have that part, right? Okay. So this is a projectile motion problem. A ball is thrown with an initial velocity of 20 at an angle of 60 above the horizontal. If you can neglect air resistance, what is the horizontal component of the instantaneous velocity at exactly the highest point? All right, so let's take a look at this in more detail. This whole idea of projectile motion. Okay. So, 20 meters per second and angle theta. And they tell us this is 60 degrees. And we're trying to figure out the horizontal component of the instantaneous velocity at the top. So we would do something like this. So think back to the lab that we did. So the velocity in the x direction versus time doesn't change, right? There is no acceleration in the x direction. So the x velocity is the same the whole time. The y velocity, on the other hand, is positive, highest point at 0, and then becomes negative. So the highest point up here, the velocity in the y direction is 0. The entire time, though, the horizontal velocity stays the same. So for projectile motion, the x velocity does not change. So at the highest point, it's still going to be whatever we find out that it is. The y velocity, on the other hand, it starts out at some value and then gets to 0 at the highest point, and then becomes negative on the way down. So this overall velocity here has an x part and an initial part in the y. If we could figure out the x part at the highest point, that's the only thing that we have is the x part. Okay? So really they're asking is what is the x velocity? So the x velocity is the overall velocity times the cosine of theta. So we've got 20 meters per second times the cosine of 60. Turns out that the cosine of 60 is also a half. The sine of 30 is a half, cosine of 60 is a half. So nice convenient numbers today. Okay, so that answers this specific question. Any questions on that part? Then I want to give you a little bit more on this idea. Okay, so you could use this fact that the y velocity at the highest point is 0 to figure out the maximum height that we can get. So the maximum height, we can look at all the kinematics equations we get. We can figure out the maximum height or the time it takes to get to the maximum height by doing this. So to get the time to highest point, we'll use the fact that the y velocity is 0 there at the highest point, and use this. Velocity final in the y, velocity initial in the y, acceleration in the y times time. So this is 0 at the highest point. So if you take the initial velocity in the y, so I'm subtracting this from both sides, divide by t or by a, that'll give me the time to get to the highest point. Now just don't forget, this is the initial velocity in the y. That's this here. Remember, the initial velocity in the y is the overall velocity times the sine of theta. So you can use, again, this fact with this kinematics equation to figure out the time to get to the highest point. Okay, let's see. And then if you want to figure out the actual highest point, same thing. The y velocity at the highest point is 0, so you can use this kinematics equation. To figure out what delta y is. Right? This is 0 because it's the highest point. So initial velocity in the y squared, so that's 0. I'm subtracting that from both sides, divided by 2 acceleration in the y. And this will give you the highest point then. Good. So I'm not saying you have to figure out the time or the delta y part, but just be familiar with the way to do that kind of problem. Let me give me a second to look at this. Okay. Yeah, that's good. One other hint for this projectile motion problem idea is to look back at the notes. If you remember, we did a problem, it's a dog that's running this way horizontally, jumps off the pier, falls a certain distance in the y direction, and we actually figured out how far over the dog got. He's a peer jumping dog question. So look back at the notes from chapter 3 too. That could be helpful for the one that's on the test. Okay, good. Does that ring a bell, that problem? If not, it's in the, take a look at the notes. Okay, good. Yeah, all right, perfect. All right, we're halfway done with the test. Almost. In a collision between a huge SUV and a small hybrid car, okay, good. The SUV exerts a larger force on the hybrid than the hybrid exerts on the SUV. Explain. So it's false, right? This is Newton's third law. If I push on the board, it pushes on me. Equal force, opposite direction. So I would say it's false. And the reason is the force is actually the same. These are it's a Newton third law pair. So in every situation like this, for every action, there's an equal and opposite reaction. Now, the SUV is a lot bigger, so the same force on the SUV doesn't experience it as much because it's larger. A more extreme example is between a truck going on the highway and a mosquito. It's the same force on the mosquito from the truck as on the truck from the mosquito. It's the same magnitude of force, but the mosquito is so much smaller, it really feels it, right? Even though it's the same force. Okay, so by Newton's third law, false, actually it's the same. For every action, there's an equal and opposite reaction. Okay, good. Hammer hitting a feather, it's the same thing as a feather hitting back on the hammer. Any questions on 7? Feel good about it? Okay. We actually watched the Mythbusters do something similar to this. If you remember, they shot a bullet horizontally and dropped one at the same time. They actually hit the ground at the same time. So I put that video on YouTube, and then from YouTube you get the link. You could watch it in class. It actually got flagged for copyright infringement. So the class video. So it's not available if you go to Turkey, the country of Turkey. You can't watch our class video. I thought that was kind of funny. So we want to know, compare the time of fall for the two pebbles. So you know from being in class that they hit at the same time. Why is that? So I guess knowing it, you get some points for that, but you have to really show why that is true. So what is the same for both of these? Well, the acceleration of the y is the same. The initial velocity in the y is actually the same. One you drop straight down, one you shoot horizontally. Oops. So acceleration is the same. One you're dropping, so the initial velocity in the y is 0. One you're shooting horizontally, so the initial velocity in the y is 0. And they're from the same height, so they have the same displacement. Whatever it is, that's the same. So we want to compare the time of the one that you shoot horizontally with the one that you just drop straight down. Okay? So you got to think about, how are we going to do this actually? Well, the tools that we have are kinematics equations. So let's see. Will this one help us to explain something about the time? So this equation has time involved, and it actually has what we're given involved. Delta y is the same. The initial velocity is 0. Acceleration in the y. This will help us compare these times. So this is 0 because they both have 0 initial velocity in the y. So 2 delta y. So this is 0. Multiply both sides by 2. Divide by acceleration in the y. That will be t squared. So if I take the square root of that, that will give me t. So I get this equation because the initial velocity in the y is 0. Delta y is the same. The acceleration in the y is the same. The time's got to be the same. Okay? Excellent. Any questions on this one? All right, very good. And the mass is not involved in the kinematics equations at all. You'll definitely see something with the graph. So this really goes back to the first, maybe the second week. So look back at all the position versus time graphs, velocity versus time graphs to tell what's going on here. Which represents an object at rest? Oops, that you can see. So an object at rest. So let's see. Looks like the first one is good, right? This is just some coordinate that doesn't change with time. So first thing, what's being graphed? Position versus time. So you're over here at some coordinate, and that doesn't change. Say that this is maybe 2 or something like that. You're over at 2, and you're staying at 2. So you're not going anywhere. Coordinate's not changing. The velocity would be 0 in that case. An object at rest, okay. This one, the position's actually changing. Right? You're at some coordinate. Some time later, you're away from the coordinate. If you wanted to get the velocity from graph this B, you would get the slope of the tangent line. So this one, the velocity is actually getting bigger and bigger and bigger. It's a parabola, right? And we know from if there's a parabola, we have acceleration. Slope of the tangent line, bigger and bigger. This one's actually speeding up. Okay. Now that's a constant velocity in the negative direction, right? Because the slope here is negative. So this would be 0 acceleration because it's a constant velocity, but you're definitely not remaining where you're at. This one doesn't actually make any sense. At a certain time, you're in multiple places. Maybe it's like quantum mechanics or something. So this graph actually doesn't even make any sense. And the last one is tempting to pick. The last one is a constant velocity. So constant velocity here means you're moving, right? The acceleration that goes along with this graph would be 0, but because the velocity is not changing. But you're definitely not staying where you're at. You're moving at a constant rate. So if this number is, say, 5 meters per second, it's not changing. Okay, so look back through the different scenarios. What does it mean to be accelerating? What does it mean to have constant velocity, that sort of thing? So this is a place to start. There'll be a graph one. Just make sure that you interpret the graphs. Okay? The slope of a position versus time graph, that's the velocity. And then the slope of a velocity versus time graph, that's the acceleration. Okay. An object that weighs 75 newtons, okay, so the weight is m times g, it's 75 newtons, pulled on a horizontal surface by a 50 newton force to the right, and we want to know, let's see, the frictional force is 30 newtons to the left. How much is the acceleration? Okay, so the weight is 75 newtons. We can get the mass if we want to. We're given some forces. Let's put everything on here that we know. A certain amount to the right. Smaller amount back to the left. Normal force and weight. And we're also told that the acceleration is something we're trying to find. Well, if you got 50 to the right and 30 to the left, there has to be an acceleration, right? There is a net force. So we want to figure out how much that net force is. Okay, so right now I got like 4 out of 10 at least. So we're given forces. We can get the mass from this. We're looking for the acceleration.